So in this question again, we have a situation of a lunar lander going around the moon. So if this is my moon, the lander is around the moon and it's going in an orbit. It says it's at an altitude of 100 kilometers. So meaning, if I were to use a different color here, meaning from here to here is 100 kilometers or 100,000 meters. We're actually given what will be the period of lunar lander if the mass of the moon is this much. So we want to know how long it takes for this to go from this point, travel through the dashed green line, and go back to the same spot that the lander was. Now this is again another centripetal question you've seen in other videos, but I'm just going to go over this again. So the centripetal force is equal to the mass of the lunar lander times the acceleration centripetal of the lunar lander. Okay, so what we're trying to figure out is that what force is responsible for the centripetal force here. It's only the gravitational force, which is equal to big G small m, big M over r squared. That's equal to small m. And instead of centripetal acceleration, we can write v squared, which is the tangential velocity, over r. Now, as you've seen in my other videos, we do get to cancel this out and simplify this equation. The small m's are going to cancel, and that shows that our calculations is irrelevant from the mass of the lunar lander. And the r here and the power of 2 of r here also will cancel. Now in this case, we are solving for the velocity because we're looking for the period. In order to find period, we obviously need so velocity is equal to the delta x over the period, and in order to find period, we need velocity and distance, and the distance around the moon can be calculated as the circumference around it. And what we can do is that we need to calculate v, and then we can find delta x, no problem, and using those we can find period. Now, so my goal here is to find v first, and in order to rearrange for v, I can rewrite v. I'm just going to write it in full. So v squared is equal this multiplied by this divided by this. So I have the big G m over r. Therefore, v is just going to be the square root of gmr. And this is a very famous equation. You will see this everywhere if you're doing escape velocities and things like that. So this is a very common equation to have. Now, if I were to plug in the numbers here, for G, I have 6.673 times 10 to the negative 11 times the mass of the moon, which is given to be 7.34 times 10 to the 22 kilogram. And that will be divided by r, which is, in this case, I know the altitude is 100,000 meters. Now, the radius of the moon can also be seen or found out. Like, you can actually find that out from it, any type of chart that is going to be given to you, and that's equal to 1.74 times 10 to the power of 6 meters, and that's just what it is. It's given. You can Google it and you can find that out. If I were to find r, since r is the distance between the center of the moon to the lunar lander, I can actually write that as 1.74 times 10 to the power of 6 plus the 100,000 meter, which is going to be equal to 184,000 meters, and that's r. And I'm just going to add that here. Okay, punch these numbers in a calculator, pause this video and try to get that number on your own. And then once you come back, you should have 1631.5 meters per second. And that's your velocity of the lunar lander over around the moon. Now on the next page, we're going to actually use the equation that solves for the period. Now that we have V, and the distance around the moon would be 2 pi r over V, so that would be 2 pi, and for r would be 1840000 over velocity, which is 163.1.5 meters per second. And that equals to 7086 seconds. So the period is equal to 7.09 times 10 to the power of 3 seconds. That's about it. Please like this video, subscribe, and if you have any questions, please comment them down below. Thank you.